start. Let's start. I'll introduce Freeke while other people coming up. Okay, so welcome to the ITC Colloquium, and today we are very lucky to have Freeke van der Voort, who is visiting us from Cardiff University. And we're specifically lucky because we tried to get Freeke for many years now, but she has very strict policy of having only 5 flights a year. And so we got rejected many years in a row. And now finally we have Freeke here among these 5 international trips. So Freeke did her PhD at the University of Leiden. Leiden University. Sorry. Okay, I'll bring up my notes because after that she traveled a lot and held postdoctoral positions pretty much around the world. So she started from the joint fellowship between Berkeley and Academia Sinica in Taipei, Taiwan. Quite a bit of commute, I guess. After that, she held also a joint position between Heidelberg and Yale. So that's I see a trend here. But she liked Germany so much that instead of going to US after Heidelberg, she moved to Garden MBA. After that, in 2020, she joined Cardiff University, and now she is their Royal Society University Research Fellow and a senior lecturer. So, as a fun fact, if you run out of science topic, which is a rarely unlikely event to discuss with Freeke during one-on-one meetings, you can ask her about her another passion, rats. And on this hang leave, I'll leave it. Okay, thank you. Okay, and on this, I'll pass it to Freeke.
Thank you. Well, it's great to be here. Sorry I didn't make it before, but better late than never. Today I will talk to you about galaxy formation using cosmological magnetohydrodynamical simulations and focusing on the effects of what the magnetic fields, what they look like, what they're doing, and also effects of ultra-relativistic particles called cosmic rays. So first, in case not everybody already loves galaxies inherently, I wanted to say why I think it's such a fantastic topic, and that is because galaxies, they form in the densest regions of the universe, and therefore, through just existing and being observable, they trace a large-scale structure, and thus they connect to things like cosmology. But galaxies don't just sort of sit there passively tracing the cosmic web. They affect their surroundings because they create these large-scale outflows that are powered by stars and by supermassive black holes, and therefore they also connect to those topics, as well as, of course, being the seat of many interesting physical processes, such as star formation, etc. So, what does the large-scale galaxy ecosystem look like? I've drawn this very unprofessional cartoon, but I think it still shows it. So the galaxy is actually fairly small compared to the scales I'll mostly focus on today, which is their halo environment. So this is the halo is sort of, you can think of it as a size that is about an order of magnitude larger than the galaxy itself. Then in the gaseous halos around these galaxies, or also called the circumgalactic medium, there's a variety of interesting processes, and I've drawn a few of them. So in order for your galaxies to grow, they have to accrete material from their environments. This necessarily has to come from the circumgalactic medium. The circumgalactic medium gets gets it through gas inflows from the intergalactic medium, and then the gas can go on to accrete onto the central galaxy. The central galaxy, however, as I said, creates these large-scale outflows, so some gas will never make it into the central galaxy because it's being pushed out by encountering these outflows, and some of the outflows may not be lost forever because they feel the pressure of the gas that they go in, that it runs into, as well as the gravitational potential. So some of it may actually end up slowing down and eventually and actually recycling back onto the main galaxy. And in a way, this is relatively common because the outflows that the galaxy creates is the gas that is most metal rich, because the metals are injected in the interstellar medium and then taken out into the circumgalactic medium through these outflows. So the gas that is the highest metallicity will have the easiest time cooling. So in a way, especially at low redshift when the metallicity is fairly high, this recycling process can actually dominate over just sort of large-scale intergalactic medium accretion. So that's just to set the scene. But today, I won't just talk about inflows and outflows that are commonly included in our galaxy formation models, but also about the effects of magnetic fields and cosmic ray feedback. And I also put in something about thermal conduction, but it's very, very much a work in progress, so it won't be very extensive, but I'll mention it at the end. This is just to show off an artist impression from a review that Rob Crane and I wrote, and to impress you with all the scales that you in principle have to think about when you want to understand galaxy formation. So so bear with me. It's 36 orders of magnitude. So I already mentioned like the large-scale structure of the universe. That is, of course, important for feeding the galaxies, but also setting where they actually form, through to galaxy scales, the interstellar medium, and then, of course, individual stars, which are absolutely tiny compared to the galaxy itself. But if you're thinking about like stellar evolution processes, the creation of heavy elements, cooling of the gas, that of course happens in interactions between atomic particles. So if you include that as well, then you go all the way down to 10 to the minus 8 centimeters, as opposed to 10 to the 28 centimeters of our observable universe. So those are the things that we should be thinking about, and we are thinking about them, but we of course can't treat 36 orders of magnitude realistically, numerically. Like it would take us many more. It would take us much longer than the actual time in the universe to compute that. So in the end, our simulations focus mostly on sort of large-scale structure, but limited large-scale structure, not the entire universe, through to galaxy scales and some of the structure inside galaxies as well. But we cannot resolve star clusters, we cannot resolve individual stars, and anything below those scales. What we do is, for those not familiar with cosmological simulations, is we start with the fluctuations that are observed in the cosmic microwave background. So we make a statistically similar universe, though not an exact carbon copy of the universe. And then we pick, because we don't want to do all of the universe, we want to do enough of the universe that we get a representative volume, but not so much that we run out of resolution to do any of the galaxy physics well. So that means that we usually limit it to about 100 megaparsec scales or so. And then what we can also do if we want even higher resolution is degrade the resolution in sort of most of this volume and increase the resolution in particular like 1 megaparsec spheres around the galaxy that we're super interested in. So that's most of what I'll talk to you about today. This is running, I can never tell, because the beginning of the universe is fairly boring. But it starts out very homogeneous. I think it's evolving. And then, so everywhere where in the CMB, the temperature was slightly higher, the density will be slightly lower, and these low density regions grow out to into the voids of the cosmic web. Anywhere where the temperature was a little bit lower, the density will be a little bit higher, and then that's where the cosmic web forms. And in the nodes of the cosmic web, the sort of yellow pixels, that's where galaxies form. And our own halo is not like those very bright yellow spots. It's more of a sort of fairly random, low mass looking object, like the one sort of sitting there away from these most massive cluster environments. So just a little bit of background about other types of cosmological simulations. These are not zooms, these are full volume cosmological simulations, and this is just to show compared to the observations. So in the dots are observational data points, and the lines are all from different suites of fairly recent cosmological simulations, and there's quite a few of them that now reproduce the galaxy stellar mass function fairly well. They reproduce galaxy sizes, galaxy properties fairly well. So then you might conclude that, okay, that's great, we've solved galaxy formation, and now we are done. However, the way they reach these conclusions, these solutions to how to form a realistic population of galaxies is actually very different. So if you look at, so focus on the left plot where I've shown you the amount of, well, the fraction of gas in the circumgalactic medium, so the gas within the virial radius, compared to what is expected if it was just following the dark matter distribution. So then if it was just the cosmic baryon fraction, then it would be 1. But as you can see, it's not 1. Which is because there's all these large-scale outflows that push gas away from the galaxy, but also out of the halo into the intergalactic medium. The main point that I want to make is how different they are. So if you focus on sort of Milky Way mass scales at 10 to the 12 solar masses, you can see that there are some simulations that predict that the fraction of gas in the CGM is 20%, and others say it's more like 60%. So these are very different solutions to the problem, and how do we even know which one we should, which one is more realistic when compared to the universe we actually live in. So we turn to the halos. This might not surprise you after that introduction, but they're actually very complicated. So many decades ago, what we thought was as gas accretes onto the halo, it will shock heat to the virial temperature of the halo. So for a Milky Way, that would be about 10 to the 6 Kelvin. And then it would sort of sit there for one cooling time, and then it would slowly get denser and cooler and accrete onto the galaxy. There's some angular momentum that it also has to lose, but then you form a gas disk, which forms a galaxy. However, both observations and simulations show us that it's actually a much more complicated system, has a lot of structure. We now know the CGM is also multi-phase, just like the ISM that we're all familiar with. And this is a cartoon from a review by Fauché-Giguère and O. And here, it's again an artist's impression. Here's the galaxy and the much larger halo. So cold gas and hot gas coexist. So cold, by the way, I try to call it cool personally. Cold is 10 to the 4 Kelvin, so it's not actually cold. So that's why some people who study molecular gas get very upset about this. But it's between 10 to the 6, 10 to the 7 Kelvin, and 10 to the 4 Kelvin is still 2 or 3 orders of magnitude in differences, and they exist in approximate pressure equilibrium. And there's all of this additional structure. So you can zoom in all the way to 1 parsec, and you will still find that at these interfaces between the hot and the cool gas, that there is a lot of structure. And of course, we don't have any hope of resolving parsec scales in our megaparsec sized simulations. So I don't have I should make a movie of my own simulations, but this is one to show you what kind of resolution we have when we do zoom simulations. This is a movie from the Auriga project that I'm involved with, but I didn't make this movie. And you can see that there's these, well, as it evolves over the full 13 billion years of evolution, we're keeping track of both the stars and their sort of optical properties. This is like a mock 3-color image of the metallicity, of the magnetic fields, of any of the gas properties. And it's this model, the galaxy formation model from Auriga, run with the Arepo moving mesh code that we use to base our simulations on as well. So we didn't change anything about the stellar feedback and the feedback from supermassive black holes, but we changed some things, like for example, taking the magnetic fields out and see what then actually happens. So I didn't originally have an acronym, but I got very jealous of everybody else who had acronyms. So now these simulations are SURGE. So again, these are variations on the Auriga simulation. So they're really very similar. But it stands for simulating the universe with refined galaxy environments. And although I don't really want to talk about what happens when you add extra resolution in the CGM today, I just wanted to show you why the name. So we've run these simulations, or most of them, keeping the galaxy the same as before, but adding an extra 100 times the resolution in the halo. And you can do this because these simulations are actually very inefficient. A lot of the processors end up waiting for the very densest gas cell to finish its calculations. That's inside the galaxy. So if you don't change anything about the galaxy, you add this resolution in the CGM, you can run a simulation that has two orders of magnitude higher resolution in the regime that I want to study, for only 4 times the computational time. So it's a very efficient way of increasing the resolution. But there are many things for which this actually turns out not to be important. There are some where it is important, especially if you want to predict observables in the cool gas. But this is what a lot of our simulations are based on. But I want to go into what about magnetic fields. So here is an image of the magnetic field strength on the left and the metallicity on the right. The galaxy is rotated such that it's edge on, and this is a projection. So you see the full 2 times the size of the virial radius projected onwards. And I think you can see the little lines through it. So this is like convolved with the direction of the magnetic field on the left and the velocity field on the right. The magnetic field is initialized at the start of the simulation at redshift 127 in the y direction, so a random direction in principle, at a very low value, 10 to the minus 10 Gauss.
Middle that would fill up the entire volume.
So the outflows are also driven by AGN, right. But the AGN don't inject additional magnetic fields, but they could.
In reality, they do.
So then the magnetic field could potentially be higher. However, we have so these magnetic fields reach equipartition in the ISM. So I think so what happens for us because we don't have any additional magnetic fields that we're injecting throughout the simulation, but we do have a lot of turbulence, and the magnetic fields get amplified to, in these objects, equipartition with the turbulent kinetic fields. The kinetic energy in the galaxy still dominates because there's a lot of rotation. But if you take the turbulence component, then they have equipartition with the magnetic field. So it would be hard for the velocities to make the magnetic fields even higher than they are in our simulations. That is the galaxy perspective, though. So in the circumgalactic medium, that's the point of why I'm showing these images. So if you think of, the easiest way for outflows to escape is the path of least resistance, which is, so if you have an edge-on galaxy, is in the polar directions. And you can see that is happening both to the magnetic field, where the magnetic field strength is the highest in the polar directions, and to the metallicity, which is also injected in the ISM and then taken out into the halo through these outflows. So you can see that there's some correlations and also some sort of large-scale coherence as well as small-scale turbulence. what the actual strengths are. So it's about 10 microgauss in a Milky Way mass galaxy, but it actually varies between 1 and 100 microgauss, which is fairly similar to observationally derived quantities. It's quite hard to get like you have to always make some assumptions if you want to derive these magnetic field strengths from observations. But if you process the simulations in a way and account for the fact that we're not resolving all of the structure in the ISM, they match actually pretty well. But I wanted to focus on the circumgalactic medium. So that's why. So here are now slices, not projections. So you can actually see what's happening in the polar direction most easily. And you can see in that, so I've switched off AGN feedback, so no feedback from supermassive black holes here. And so this is only, this is a galaxy evolving with only stellar feedback-driven outflows. In the top, you can see the magnetic field strength. So in these polar directions, they can be a microgauss or even more, whereas in most of the volume, because of course the volume is not primarily these outflow directions, because the halos are 3D, it's mostly away from these outflow directions. And most of the volume, the magnetic field strengths are much lower, below 0.1 microgauss. And that means that if you compare the magnetic pressure to the thermal pressure, you can have some localized areas where the magnetic fields dominate the pressure, but in most of the volume, the magnetic pressure is orders of magnitude lower than the thermal pressure, which is mostly from the hot gas. Yeah?
Question. So you said you don't have thermal feedback, the AGN feedback. So am I reading these plots correctly that most of the feedback actually appears to be coming from larger cylindrical radii in the disk? Because
Yeah.
it seems like, that's where the strong magnetic field is coming from, larger radii, whereas in the middle, there's like, a weaker.
So this correlates with the density. So because there's also compression. So as the gas cools, the density will get higher, and then the magnetic field strength is higher. Whereas if you have a just blown outflow, the density will be very low, and therefore the magnetic fields will have expanded and be low. So I have some comparison. So this is the same model, but with AGN feedback. These are thermal bubbles that heat the CGM directly. And also another one, this is a different galaxy formation model from the illustrious TNG project. And they are different because there's different feedback, but they, in sort of the global structure is very similar. We still have some localized areas where the magnetic field dominates, but the volume is dominated by the thermal pressure. I wanted to say that not everybody agrees about this. So we have, on average, thermal over magnetic pressure ratio of about 20. There are also other simulations, such as the fire simulations, who have much lower magnetic field strengths in the circumgalactic medium. And this can be due to a variety of things, numerical as well as like specific modeling choices for the outflows or specific modeling choices for the magnetic fields. Or something about this, these are not grid code, like ours is a grid code, but they don't use a grid code. So there could be all sorts of, there are a lot of differences, so I can't really pinpoint what difference is responsible for this. But I just wanted to say that I am going to tell you what we predict as the effect of magnetic fields, but there are other projects that find no effect of magnetic fields. So the jury is out, I guess. So in order to convince you that, of course, we are the ones that are right, or at least why we believe that we have like decent magnetic field strength, is if you calculate the rotation measure, which is just this is an observational property. It's the integral. So use background objects that go through the denser halo, right? It's denser than the intergalactic medium, I guess. And it's the integral for the full line of sight of the electron density and the magnetic field along in the perpendicular direction, the parallel direction as a sight line, but this includes any field reversal. So if you had a perfect if you had as much magnetic field lines away from the observer as towards the observer, your rotation measure would be 0. So it's really important. So it's not just about what the field strength is, it's also about what the structure is. And that's why it's very important to use the simulations to predict the observables rather than just compare field strengths. So Rudiger Pakmar has done this. So this is the rotation measure in our simulations as a function of radius. When we published this, there was only upper limits. It was very easy to match upper limits, so everything was good. But now there have been, so people are really observing these rotation measures very efficiently with, so the blue one is from a large-scale LOFAR survey of polarized background sources, and the pink one is an individual fast radio burst that was detected in M81's halo. And I've just put those values on here as well, and our simulations at least are in agreement with those.
So your assumption is these belong to the host galaxy of the source? Or is it along the line of sight?
This is along the line of sight, yeah.
So how do you know where they come?
Well, so we believe the way the observers have taken these different contributions out, which of course has some. We've also actually, in a different study, we compared it to the host contribution, which was also a reasonable match, but I didn't bring it today.
Where would you set the boundary between the host and the
So for this, we don't have to do it because the hosts would be like really here in the central 10 kiloparsec or something. But if you wanted to, if you did an observation,
in the analysis of the rotation measures,
the observations.
Curious what they've done.
Yes, I don't know in enough detail to answer that question.
But you believe observers?
No, I mean, I'm telling you what I have done, and then we can all make our own conclusions. If they are right, then so M81 I think is fairly easy because that one was very far away from the star-forming galaxy itself, and clearly embedded in the H1 disk around the galaxy. So so that's included in that data point. There's no specific splits. Of course, for the LOFAR results, well, it's also a very broad 100 kiloparsec bin, so you can hide a lot in there. But like they're using any polarized background source, and I don't know enough about how hard it is to take that contribution out. I think the IGM is fairly easy to take out because there's a very clear relation between, so you can on average predict what that would be if you know how long the path length is.
Yes, I think that's a good question, like about the rotation measure from the observation. So for instance, even horizon telescope collaboration, was that just, I think up until now, we don't have a very good confirmation that we measure that, or like error bars and inconsistencies. But my question is more on the theory side, like since different feedback models may lead to different magnetic field structures, could that be that we use this rotation measure as an indirect way of getting to the feedback models?
I think with much better statistics we will get, so the rotation measure in combination with the dispersion measure, which only traces the density, so rotation is density and magnetic field, and the dispersion is just the density. We should be so with much larger samples, of course, with like a handful, you can't really rule anything out. But with much larger samples of these sources, I think well, not me personally, but I think what we as a community will be able to put constraints, and they should just be getting better and better as time goes on, because they're really finding a lot of FRBs now with new telescopes. So. Of course, if they're for CGM, you want them to be localized and you want to know exactly where they go through the foreground halo. So that's of course a little bit more tricky than just finding an FRB, but I think we'll get there. It's also the blue upper limit is also from a single FRB that was very well localized and went through the CGM of a foreground object. Okay. So I hope I still make it to the end. But let's talk about, so that, I just wanted to show you that I don't only look at the CGM, but the galaxies themselves as well, because of course they're very important, because inside the galaxies are these sources of feedback. So if you change the galaxy, you will also change especially how the stellar feedback is distributed. So these are the galaxies from my simulations, left without magnetic fields and on the right with magnetic fields, and we get larger disks when we have MHD included. This now means that the star formation will happen like in different locations than if you had a more compact disk. So this then also changes the outflows, which is just something important to keep in mind when you're, so the beauty of cosmological simulations is that we have like so many processes included, but the downside is that we have no strong control over any of it. And so a lot of different things might be happening at the same time, and it can be really hard to disentangle them. But we do our best. So this is then the effect that these magnetic fields have on the circumgalactic medium properties. So in the top, you see a simulation without magnetic fields, and the bottom has magnetic fields. This is the same one without AGN feedback that I showed you earlier. And you can see that there is more filamentary structure. The pressure is a lot smoother with this additional magnetic pressure. And the sort of small-scale structure is, it's a lot more filamentary rather than just sort of looking more randomly turbulent. So does this matter? So when we look at the metallicity, which I've already told you is very important for how the gas is cooling and therefore how the galaxy is being fed, it changes a lot. So that's why I took this one out to show you in the largest way possible. So on the left, without magnetic fields, on the right, with magnetic fields. So you can see that in the case without magnetic fields, the metallicity of the entire halo is much higher. It's much better mixed, whereas with magnetic fields, the metals stay much closer to the polar direction and much more associated with the outflows, whereas most of the CGM is remaining relatively metal poor. Why this is happening is then another question. So this could be both because the outflow properties are different, because so it's not just the stellar feedback happening in different parts of the galaxy, but also with magnetic fields, we have a much thicker neutral hydrogen-dominated disk around the galaxy, which also helps collimate the outflows. So we might just have sort of set at small scales a much more collimated outflow being driven. Or the other option, or of course a combination of the two, is that we actually have less mixing between inflows and outflows, or just less turbulence in a simulation with magnetic fields, because magnetic fields help to suppress any sort of instabilities and probably limit turbulence. So Hille has worked on this. So he used one of the surge simulations to re-simulate it, but after injecting a scalar in different regions in the halo in order to see how this blob of gas, like it's not even a cloud, right? It was just randomly selected regions, how it would evolve. And he did this in a variety of ways, selecting inflows, selecting outflows, etc., and then correlated everything with everything, which is the bottom row here, and found that most of so how this dye then spreads throughout the halo is mostly correlated with the velocity dispersion. You can also look at the directional, like how well the elongation of this dyed region correlates with specific vectors in the simulations. So if it was completely uncorrelated, you would find this black curve. You can see there's some alignment between how a region of gas mixes with its environment, with the velocity and with the magnetic field, but the strongest correlation is with the the velocity dispersion. We had to do a trick because velocity dispersion doesn't have isn't a vector, it's a number, but you can calculate an x, y, and z velocity dispersion, which gives you a vector that only exists in the positive octant. So that's why this is like slightly funky compared to just regular vectors. It's only it's the absolute value of vectors that we've correlated. So then if you look what the velocity dispersion is for all of the gas in the halo in these simulations, left without, right with magnetic fields, you can see that there's almost a factor of 2 difference. I've drawn these dotted lines just for you to compare. So in one case, we're at 100 kiloparsec away from the galaxy. In one case, it's 45 kilometers per second. Velocity dispersions. In the other case, it's like 27 or so. So this is a huge difference, and that at least partly explains the mixing differences, though I'm very much not ruling out that there's also a galaxy outflow difference as well. The color is the log density, so how much gas is in each individual pixel. So the black line is the median, and the colors are the full spread, with red being only one of our resolution elements, whereas blue is like thousands of them or more. Yeah?
What the sparky wedges, are these satellite galaxies, or what are the...
These ones, or
Yeah.
I think so, yeah, but I haven't specifically looked into it. This halo has, I mean, it must be, because this halo has a satellite that is very gas rich at 175 kiloparsec. So I haven't checked, but yes. Yeah.
Sorry, just very quickly. So did you make a phase cut in terms of like density or temperature for these plots, or is this just all the gas?
This is all gas.
Okay.
Yeah. Let me move on and stop talking about magnetic fields because that's so much fun stuff. Okay, let me say something about. Okay, so Andy Cook, who's been working with me. So everything I showed you before is all for a Milky Way mass halo, because that's where we live, but also they're really fun because everything is important in Milky Way mass halos. But Andy has spent a lot of time expanding this to cover a much wider mass scale. So we have dwarfs on the left at halo masses that are about a factor of 30 lower, and up to small groups of 10 times more massive than the Milky Way. And you can see that that any differences, we can, for example, look at the metallicity here. So this one would be a Milky Way difference, and for things slightly smaller than the Milky Way, we also see huge differences. But for our tiniest dwarfs, the differences disappear. Basically, they don't create very strong outflows. In our galaxy formation model, again, reality might disagree with us, but that is what we have. And then on the right, you can see for very massive halos, the thermal pressure is so high that we also end up finding no strong differences with and without magnetic fields. However, so that's for the global properties. But if you look, so this is one of those halos, and you can see that there is a very giant satellite orbiting inside this halo. And so Thomas has been working on this, but he's done it the other way around. So magnetic fields are now on the left, and no magnetic fields are on the right. And if you look at this satellite that's passing on top of the central galaxy, you can see that the ram pressure strip tail is looking very different. And Thomas has isolated this and quantified this. So here you can see how they look different in density, temperature, metallicity, and the vorticity. We can again focus on the metallicity because it's very strikingly different. You see there's a much larger region behind this. So the satellite is traveling in the -z direction. A much larger region of high metallicity behind the satellites without magnetic fields. Then there is much smaller tails and much more confined metal-rich tails behind the satellite with magnetic fields. if you look at how much mass is being lost by this particular satellite over about a gigayear of evolution, without magnetic fields, the gas inside that's part of this satellite halo, so this is not the ISM, it's the CGM that's being lost, is about twice as much as in the case where we have magnetic fields included. And if you then check through, like using tracer particles, I don't want to go into how that works too much, but you can see how much of the tail that you end up with was originally from the satellite's halo or from the host halo. So the satellite that has lost most of its gas because it didn't have any magnetic fields also has more gas mixed in. So this satellite's tail is much better mixed and much more massive because of this additional stripping and additional mixing. Yeah.
The effect is not just hydrodynamic, actually, the most important effect is thermal conduction, if they are. And so we see that in clusters of galaxies, actually.
Yeah, so we don't have, these simulations don't include thermal conduction.
But that could be very important.
So we will find out in the future, and I will show you, well, I guess I won't really show you. We have like a preliminary simulation, and then we found that the method we were using wasn't energy conserving. So we've gone back and we're now doing it again, but properly. So, but yeah, you're right, that might really change things. So we see some evidence of magnetic draping that can explain at least partly how this works. So again, this satellite is traveling in the minus z direction, and you can see that the magnetic fields are draping around this galaxy, sort of protecting it from being stripped. And then you can also see that the magnetic field lines are aligned in the tail direction, and this is also seen in observations of ISM stripping in clusters, which is very different from this. The process is the same, but the objects are very different, and the densities that we're probing are far too low to be easily observable. So I have like no time left, but I promised cosmic ray feedback. So I wanted to show you some things that we've been working on. This is work that's done by Rebecca Bieri, who's in Zurich. And here I'm already showing you 3 different halo masses from 10 to the 10, 10 to the 11, 10 to the 12, so Milky Way mass, and 10 to the 13. And we find the same thing for the Milky Way as with removing magnetic fields, is that the disk ends up being more compact. I think it might be more insightful to look actually at the star formation histories. So this as a function of look-back time. If you look at the top row, which are the galaxies that are smaller or lower mass than the Milky Way, you can see that the difference between the pure MHD simulation, which is dashed, and then the one with cosmic ray feedback included are clearly there. So the star formation rates are suppressed when we have this additional source of feedback, but which I guess is in a way maybe not surprising, because we did add feedback which can result in outflows, but it doesn't have to. So if we look at the higher mass objects, you can see that there's basically no, well, there's always some cosmic fluctuations, but there's basically no effect that we see in our simulations in the way that our cosmic rays evolve. Here you can see what that then looks like for the radial velocity. Again, going from low to high mass, you can see that there's huge differences. So pink is outflowing, blue is inflowing. So there's huge differences for the halos that are 10 to the 10, 10 to the 11 solar masses, but much smaller differences at high masses. And then that relates to differences inside the halo. So now this is a plot where we're only comparing 2 halos, so the smallest dwarf and the Milky Way mass halo. And you can see that if you focus just on the red lines, which is the Milky Way, you can see there's basically no differences. The CGM properties, at least on average, are the same. But for our dwarf halo, which is now creating outflows, which are suppressing the star formation, but it's not just doing that, because this additional pressure term that's due to these relativistic particles is able to support, can dominate in the halo and is able to support the gas, which means that if you look at the temperature, which in the case without cosmic ray feedback was close to the virial temperature of these low mass objects, with cosmic ray feedback, it's actually just sitting at 10 to the 4 Kelvin, which is about as low as the simulation will allow it to cool, and it's being supported by this additional cosmic ray pressure gradient. We have done other things, like vary how exactly our model for cosmic ray feedback. Of course, we need, well, nobody fully understands cosmic ray physics, so in that sense, I'm in good company, but you can, so you have to model it somehow, and so cosmic rays will obviously move as the gas moves, just pure advection, but they will also move with respect to the gas, which we model with a diffusion term, but then what the value for this diffusion should be is at least by an order of magnitude uncertain. So if we now pick something that is able to, that allows the cosmic rays to diffuse 10 times faster than our fiducial model, so which is sort of, if you're interested in galaxies, which is high density, you might think that the fiducial value of 10 to the 28 is like fairly reasonable. But if you're interested in the CGM, which is sitting at much lower densities, so these are simulations that do much fancier cosmic ray transport. So that's why they have an effect, like the diffusion coefficient comes out rather than is being put in by hand. Then you can see that maybe in the halo, where the densities are low, a higher diffusion coefficient is more appropriate. So if we do this, this is, I should be showing you this for the dwarf galaxy because it'd be more clear. But let me cheat and show you the simulation. So Andy Hannington has been doing this. So these are simulations where we've switched off energy losses through scattering with Alfvén waves in the magnetic fields. Don't worry too much about it. So in our fiducial simulations, the cosmic rays lose a lot of their energy through interactions with the magnetic fields, which is why they don't have a strong effect in Milky Way mass halos. If we switch that off, and it's uncertain, so it's not even like, it's not even just a numerical trick. You can say like, well, these sort of models, brackets, we think one is more realistic, but really we don't know. Then there's no loss or not much loss of cosmic ray energy, and you can build up. So if you look at the second row, you can see the temperature. So on the left is no cosmic ray feedback. In the middle, you can see the fiducial 10 to the 28 per square centimeter diffusion coefficient. And you can see that the inner CGM is very low temperature because the cosmic rays are not lost, but they diffuse out, but they don't diffuse out super fast, and they really support the inner CGM, which can then cool down to 10 to the 4 Kelvin without collapsing onto the central galaxy. If we increase this diffusion coefficient to 10 to the 29, the cosmic rays naturally diffuse much further out. The pressure gradients is set over a much larger scale, and you get this. The cosmic rays dominate less strongly, but over much larger distances. So you get a very different CGM structure if you do that. Here again, I want to mention that some people disagree with our conclusions. So this is simulations from the FIRE collaboration that where I'm showing you the temperature, and this is one where they have cooling losses included, so we basically get no effect at Milky Way halo mass scales, and they have a huge effect, so they don't have a hot halo without cosmic ray, well, they have a halo without cosmic ray feedback, but they lose this because the entire halo becomes cosmic ray supported. So in a way, we're seeing the same behavior, but in different ways, because we only get this if we switch off cooling losses, which are included here. But their magnetic field strength is lower, and therefore the cooling losses will be lower than in our simulations, which have higher magnetic field strength, because it's this interaction with the magnetic field that's causing it. Okay, this is all fascinating. One last point on thermal conduction. So this is a cluster halo, and therefore very different from anything I've shown you today. But this is actually a correct model, so I didn't want to show you our wrong simulations with an incorrect model. So Rosie Talbot has been fixing the model, and it now works. So we can run thermal conduction with hierarchical time steps in cosmological simulations. But she's focused on the intercluster medium, so therefore it's quite different from what you've seen before. But if you look at just what the temperature looks like in a simulation without thermal conduction, and then two flavors of thermal conduction, you can see that it can actually have a huge impact on the structure and the scatter that you find. So here's the scatter in temperature is quantified here. So the scatter is much larger in the standard simulations than in the ones with thermal conduction included. And so we have some preliminary results on lower mass systems, but they are wrong, and therefore we'll have to wait and see what happens when we run it with Rosie's corrected model. And that's where I'll stop today. Thank you.
Okay, questions?
There is one additional effect that is very important, and I don't know if you plan to include it, but that is radiation pressure on the dust that could drive outflows, because the cross-section for dust is 100 times, I mean, the solar metallicity, it's 100 times the Thomson cross-section per proton mass, so it's 100 times more than the standard electron scattering cross-section. So it can drive outflows even if the luminosity is sub-Eddington.
Yeah, I mean, indeed, and I think people have included this and have found, especially in certain, I think especially at high redshift, that this can be very important. I think at low redshift, which is what all of this was, I think people have been finding that it's not as doesn't have a significant impact. But yeah, we have not included it, and I think. We're not immediately planning on including it. I do think that any radiation transport is like useful and also very necessary for correctly predicting observables and stuff. So yeah, it would definitely be something worthwhile to focus on. But then they do take longer to run. So yeah, worthwhile doing for sure.
Yeah, thanks for the great talk. Are there, do you think there are magnetic field strengths that can be ruled out based on the morphology of stripped gas in our galaxy? For example, imagine like a stream or hypervelocity stars. We see that there is structure, but there's not infinite structure. So can you turn that back into a constraint on, well, the magnetic field can't be like 100,000 gas? Yeah.
In the tail, or you mean in the galaxy?
Tail. Yeah.
I think this. Well, I don't know, but I think it would be interesting to try. It might be because a stripped tail might depend then mostly on the process of stripping rather than on the process of so like rather than the standard turbulent dynamo. So you might end up with simulations being like fairly in agreement about what the structure should be. Of course, within the limitation of can we even resolve it, right? Because if you see any sort of small-scale structure on parsec scales, there's no hope with any of these simulations. I think maybe field strengths would be more constraining, especially field strengths in the low-density gas, where it's harder to. So in the galaxies themselves, it's quite to get the turbulent dynamo going and saturated is much easier than in the low density gas, which depends more. Well, is there an in situ dynamo in the halo? Our simulations say a low redshift, maybe there is, and any outflow properties. So, interesting to think about.
We have more questions.
Do you have any sense of what would be detectable in terms of H1 emission pretty far from the galaxy in terms of trying to map out these structures?
Well, with SKA, it will be a lot easier. I mean, people are already seeing, so they're seeing H1 with like FAST, for example, and also Meerkat. And I've read several of the papers, and I think they're actually not necessarily in agreement with each other. Like one of them, and you'll have to forgive me for me not remembering which one, is finding very like smooth disks that then suddenly, well, maybe not disks, smooth H1 distributions that then suddenly cut off, and they don't really see a continuing trend. They sort of see the density falling off, and then there's a strong drop, and the other one didn't really show that. I know that there is a group using the standard Auriga simulations to post-process them and to predict them, and I think they are saying that the structure in the simulations is more than they see in the so the observationally processed simulations show more structure than the observations. So if that turns out to be indeed the case, then I think that might be a great way to go about ruling some things out or making us think about like why could those things be the case.
Okay, there quick last question.
Very quick. So the last slide about the thermal conduction. So maybe you just haven't had the chance. I'm wondering if you've looked at the possible presence of cold fronts, so contact discontinuities in these simulations, because there's a number of more idealized MHD simulations of clusters, including thermal conduction, which shows that even if you have conduction anisotropic at full Spitzer, it obliterates the cold fronts. The magnetic draping effect doesn't work because of instabilities and things, which may imply actually, as suggested by the Whistler panel here, that conduction in the ICM may be very highly suppressed. So I don't know if this is something that
So, yeah, this is almost, well, we haven't gotten there yet. I think it's the plan. We just got the methods paper out. Oh, it's on the archive. It's not yet accepted. I think we will spend a lot more effort into analyzing the cluster. We also have a much larger sample now, so analyzing the cluster simulations as well. But yeah, I do worry, because if this also happens in lower mass halos, then we also wouldn't really get the multi-phase structure that we sort of know exists. So yeah, it'll be interesting to see how that turns out.
Okay, awesome. Perfectly on time. Let's thank Freeke again. See you in half an hour.
Ah, yes.